In this video, we'll look at a linear first-order differential equation. We can see that it's linear because it involves y prime and y, and not in any unusual algebraic way. We've just got some coefficient of y prime, we've got a coefficient of y that only involves x, and we're not doing anything like squaring y or involving it in algebra in any non-trivial fashion. In order to solve a linear first-order differential equation, what we want to do first is to get it into standard form. And that means the coefficient of y prime should be 1, and then whatever coefficients remain, anything involving just x's should be on the right-hand side. In this example, we'll need to divide by e to the 3x throughout the expression in order to get it into standard form. When I do that, the terms on the left side cancel, but we'll get a new term on the right, that over e to the 3x. It's perhaps a little more natural to write that as x times e to the minus 3x, because we'll have to integrate that right-hand side eventually. In order to solve it now, you're going to need to find an integrating factor, which requires first identifying what the coefficient of y is. In standard form, that's called p of x. And in this case, p of x is just the function minus 2. The integrating factor, which is called mu, the Greek letter, is equal to e times the integral of p of x dx. In this case, I need to integrate minus 2. Simple enough, it's minus 2. I don't need a constant of integration because we're looking for just any integrating factor that will work, and we'll take it to be c. We'll take c to be 0. So our integrating factor will be e to the minus 2x. And then you need to multiply through your original equation by mu. So in this case, here's my equation in standard form. I'm going to multiply the left side terms all by e to the minus 2x. Don't forget to do it on the right side as well. So I'll have these products of these two exponentials. And using laws of exponents, same base means I get to add exponents, so I'll have e to the minus 5x now. The left-hand side will automatically be a derivative if you've done your calculation correctly. It'll be the derivative of a product of mu times y. And let's just check. If I differentiate my integrating factor times y, I've got to use the product rule. I'll leave this factor alone and take the derivative of y, that's y prime. I'll leave y alone, and now take the derivative of the exponential, and that gives us the minus 2 e to the minus 2x. So that left-hand side now is being realized as a derivative. That right-hand side is just copied again. Having that left side be a derivative is great, because if I integrate it, I get back to where I started, what I'm differentiating. So integrating the left side gives me the expression in brackets there, and I now need to integrate the right-hand side as well. This is a classic example of integration by parts. We'll take u to be x. dv has to be e to the minus 5x, including the differential dx. Differentiate, and we'll see that du is equal to 1 times dx. And integrate to find v, and that requires dividing by minus 5. In the exponential form, let's run out the integration by parts formula. Now u times v, and then minus v du, subbing those things in from the box. And we have something now that's reduced the power. We don't have an x anymore, and we'll be able to integrate this expression. So integrating e to the minus 5x gives me another factor of minus 5. And simplifying, we'll have this expression with the x in it. We'll have the expression now with minus 1/25 times the exponential, and then the constant term. Do not forget the constant of integration here. It's crucial. So on the left side of my equation, I have e to the minus 2x times y is equal to this complicated expression on the right. We now solve for y by dividing by the exponential that appears on the left. So I've got to divide everything on the left-hand side by e to the minus 2x. Doing so is the same as multiplying by positive 2x as the exponent. So we're going to multiply here by e to the 2x, multiply here by e to the 2x, and don't forget to multiply the constant of integration by e to the 2x as well. Everything gets multiplied by e to the 2x. Simplifying and adding powers here, we'll have e to the minus 3x, e to the minus 3x here, and we'll just carry the constant times the exponential here. And there are explicit general solutions to the differential equation that we started with. Now it's worth discussing this a little bit. There are a couple of terms in here that are what we call transient terms. And transient means they are short-lived terms. They go to 0 as the variable increases, as x goes to infinity. Two of the terms that are transient are the ones with the decaying exponential function. This function here will go to 0 as x gets large. This will go to 0 as x gets large as well. So that's transient, and that's transient. The term that's attached to the constant of integration goes to infinity, assuming that c is not 0, goes to infinity as x gets large, and is pretty significant, and in fact dominating this expression for large values of x. What happens as x gets large to the answer is called the steady state solution. In this case, the steady state behavior of my expression as x goes to infinity is that my y approaches more and more like this third term. So there's two terms. As x gets large, these highlighted terms go to 0, and then the second term here, or the third term rather, is called the steady state behavior of the system. My y value will look more and more like this function here. So that term that was attached to the constant turned out to probably be the most important part of the expression in the long run.